So moving on to our webinar, Dr. Melanie Vanderhoof is a research geographer with the United States Geological Survey, Geoscience and Environmental Change Science Center based in Denver, Colorado. She received her PhD in geography from Clark University in 2014. After a postdoc with the US EPA, she joined the USGS in 2015. She uses satellite imagery to understand how ecosystems change over time. Her research focuses on improving our ability to track changes in the quantity and distribution of surface water across the landscape and understanding how climate extremes and climate change impact wetland, lake, and river dynamics, as well as tracking wildfire extent, severity, and patterns of post-fire recovery. On behalf of MAGIC, we thank you for being here today and sharing your knowledge with us. Without further ado, Dr. Melanie Vanderhoof.
Great. Thank you, Michelle. And thanks for everyone for taking the time out of their day to come, and for Michelle for the invitation. I was fortunate enough to work with Michelle back in 2019 out at the USGS in Denver. Today I'm going to be talking about some surface water research. And as Michelle mentioned, I'm a research geographer. And essentially, I use satellite imagery to understand how ecosystems change over time. Although I end up applying that satellite imagery to a lot of different topics, I'm going to be talking about the water research component today. All right. So regardless of kind of what kind of project or what kind of topic, most of my research kind of follows a really similar format in terms of moving from satellites to products to applications. And that kind of high level general format is kind of first selecting a satellite with the type of data that's best matched to answer kind of the research questions we have at the very end. And then using data bands and combinations of bands from those satellites, building statistical models or training an algorithm using that data, for example, to map surface water extent or burned area or land cover, et cetera. And then applying that statistical model or algorithm to a time series of satellite data. And what we get out of that is a classified time series, so a data product. And that data product might be land cover or burned area, surface water extent, impervious surfaces. They're all kind of following that general flow, workflow. And then the last part of that is using the classified imagery with other data, whether that be field data or other remotely sensed data products, to ask and hopefully answer interesting science and management questions. So that's essentially the workflow that I'm going to follow with this talk. So I'm going to share with you two algorithms, Sentinel-1 based and a Sentinel-2 based surface water algorithms that we recently developed to map open and vegetated water. This work was published earlier this year in Remote Sensing of Environment. And then I'm going to share a little bit on two different projects where we're applying that surface water algorithms to support those projects. So the first is projecting the impact of climate change on surface water dynamics. And the second one is a floodplain management project that's fairly close to you guys in Memphis. And I'll just note that the two applications will both eventually be published, but are not yet peer-reviewed and published, but I find it much funner to talk about ongoing research than published research. So, so bear with me that they're both still kind of in draft format. All right, so if we kind of step back for a second to think about surface water extent, when I'm using the term surface water extent or inundation, I'm talking about lots of different features, including rivers, lakes, wetlands, reservoirs, ponds, temporary inundation and flood-prone areas, et cetera. And having a robust and accurate data set that can represent inundation dynamics at an appropriate spatial and temporal scale will really have kind of widespread benefits for managing flood and drought risks and impacts, managing aquatic habitat, monitoring water quality, guiding recreation, as well as informing kind of land uses that have water and surface water as a big component of it, such as irrigation and agriculture and drinking water. But there are a few challenges in remote sensing that are very specific to surface water. The first is that surface water can be quite highly dynamic. So, you can have a big rain event and you have a change in surface water extent. You've got seasonal changes. And so that means that something like land cover, where we might be able to use lots of images or maybe even the phenology over time in those images to come up with a classification. Surface water, we really have to classify each image individually. One of the other challenges is that the peaks in surface water often co-occur with cloud cover. So we can think about a big hurricane coming up the coast, dropping lots of rain, causing lots of flooding. But when we look at it with optical satellite imagery like Landsat or MODIS, we just see a mass of clouds, and it's hard to get information at those moments where we really want it. Spatial resolution is another really substantial challenge that's very specific to water. So if you look at the figure here on the right, can you see my pointer? Hopefully. The blue box here is the size of a Landsat pixel. So it's 30 meters by 30 meters. The red box here is 20 meters by 20 meters. This is the size of the algorithm I'm going to be talking about today. And this light blue box is the size of a planet scope, a 3-meter resolution pixel, which is a CubeSat. And so you can see that as we start to get into edges of lakes and small water bodies, we start having a lower and lower probability that we're going to be able to capture that feature, because it's just comprising kind of a lower and lower percent of a given pixel. And that problem gets way worse when we move into river landscape. So this is a river in Iowa. It's about 9 to 15 feet wide. So if you kind of picture that in your head, that's a pretty decent sized river. And yet if we compare it to some of these pixels, we're having a pretty darn hard time mapping that, especially as things get any coarser than 30 meters. One of the last challenges with water is that a lot of water is covered with vegetation. If you think of like a cattail pond or tidal wetlands, and that means from a remote sensing perspective that those pixels are mixed. So a single pixel is going to be a mix of water and vegetation. And that gets pretty tricky to pull out the water component. And that means that those vegetated water is kind of rarely mapped by most water data sets. So what we've got kind of in the bucket of existing products that are kind of the best we've got right now is there's a global surface water product out of Europe, a JRC, that's primarily mapping open water at 30-meter resolution. And then USGS also has a DSWE, dynamic surface water extent algorithm, that's again using Landsat and does quite a bit better job of pulling in that vegetated water. But those challenges kind of are really still persisting and have motivated us to come up with kind of better algorithms here. So for this approach, we used Sentinel-1 and Sentinel-2 satellites. Both of these satellites are launched and managed by Copernicus, which is the Earth observation component of the European Union space program. Both satellites are a series of 2 satellites that fly in complement with one another. So Sentinel-2 is the first was launched in 2015, the second was launched in 2017. They are multispectral optical satellites. They have 13 spectral bands. The bands overlap quite a bit with Landsat, but they lack the thermal bands out here. And the band resolution ranges from about 10 to 60 meters in resolution. Sentinel-1 is the other satellite. Again, it's a series of 2. Each was launched a year prior to the Sentinel-1. And Sentinel-1 is a C-band synthetic aperture radar satellite, or SAR. And for those of you less familiar with SAR data, When an optical satellite like Landsat or Sentinel, they fly over the Earth and they just collect, passively collect reflectance information about the amount of reflectance in which band lengths and the intensity of that. A SAR satellite flies over and it actively sends pulses down to the Earth, and then it collects information about how much, the direction, the magnitude of that backscatter that's making its way back to the satellite. And Sentinel-1 has a dual polarization, which essentially means that we get data in two bands. We have a VV, you can see an example of the VV right here, and a VH right here. And the return interval with both of them flying is 12 days, but unfortunately the second one had a major power outage at the end of December 2021 and is no longer collecting data. So SAR data can be a little bit trickier to work with and a little less intuitive than multispectral data, but there are some pretty big advantages to including it. Those advantages are particularly large when it comes to cloud cover and snow cover. So on the left here, this is an example of both images were collected on the exact same day. You can see Sentinel-2 has a big cloud, as well as some cloud shadow there. When we have a cloud there, we essentially lose all of our information and data about what's happening on the ground. But you can see here on the left, this is what the Sentinel-1 image looks like the same day, and we retain all that information because the SAR satellites can see right through those clouds. And the same is actually true for snow cover. On the right here, you can see the Sentinel-2 image. It's going to be pretty darn hard to look at that image and map surface water. But on the left, this is collected the exact same day, and we still have most of that data intact. So to develop the algorithm, we selected 12 training sites across CONUS, and we collected training data on open water. So by open water, we're including lakes, ponds, reservoirs, rivers, bays, and oceans in here, and then also vegetated water. So wetlands, riparian corridors, temporary inundation, flood-prone areas, etc. And we trained the algorithms on near-date Sentinel-1 and Sentinel-2 image pairs, 8 pairs per site for each of the 12 sites. And we developed 2 separate algorithms using gradient-boosted classifiers, which is essentially a machine learning algorithm that uses a series of decision trees, but learns from each prior tree. So it's trying to reduce the error between each tree. We ran a variable selection process for each algorithm where the selected variables were based on their contribution to reducing the model's root mean square error. And something a little bit different in terms of our approach was that we included both topographic and meteorological variables as potential variables to help the models find where on the landscape water tends to collect and when that water tends to be on the landscape. And so on the bottom here, you can see these are the variables selected in the Sentinel-1 and Sentinel-2 models with the variable importance on the y-axis. But I just included this, not expecting you to read sideways here. But in brown here, these are the variables that are topographic variables that were selected. And in blue here are the meteorological variables that were selected. And the other ones are just kind of spectral and backscatter variables. So it did, both of those types of variables did seem to be consistently selected by the models. So the models seem to find them helpful. And then we applied those models across the 12 areas for a 5-year time period from 2017 through 2021. And in doing so, processed close to 43,000 Sentinel-2 images and about 10,500 Sentinel-1 images. All right, and then we validated the algorithms using commercial imagery. So PlanetScope imagery, which is a series of CubeSats that are 3 to 5 meters in resolution, as well as Maxar, primarily Worldview 3 and 4, which are closer to kind of 1 to 2 meter resolution. So on the top line is Sentinel-1 algorithm, and on the bottom is Sentinel-2 algorithm. And you can see our leftmost boxes here is our open water omission error and commission error. And we had very low error rates in the open water, which is kind of in line with what we'd expect. It's not too difficult to map kind of large open water bodies. However, subpixels, mixed pixels like vegetated water are quite a bit trickier. And so kind of as expected, our error rates are a bit higher here. And we're doing kind of better with Sentinel-2 than we are with Sentinel-1. So our overall accuracy, if we're mapping just kind of water and non-water, is about 86% for the Sentinel-1 algorithm and 93% for the Sentinel-2 algorithm. And on the right here, you can kind of get a sense. This is the open water percent is overlaid on top of the vegetated water percent, which is kind of in the greenish. And you can see kind of how the models are performing in places like coastal wetlands. Here, the second line down, the third line down is like a river-dominated landscape in Missouri. And the bottom line is showing some forested wetlands in Maryland. And so with this data, we can start to do lots of interesting things and look at kind of different components of water on the landscape. So for example, one thing we can do is just look at how dynamic different water bodies are. And this can give us information about the hydro period of water bodies. And so this is showing us is basically collapsing all of the classified imagery over the 5-year period just for the open water percentile. And so if we look here in the upper left at the Arizona panels, this shows you that this lake in Arizona sometimes is basically shrinking and expanding over time. And so we can look at how dynamic it is, and we can also compare how the two different algorithms are mapping that hydro period differently. We can also, instead of looking kind of at individual pixels or individual water features, we can look at entire areas over time. So on the right here, these are tracking open and vegetated water for the two different algorithms for blocks that are about 4,000 kilometers squared. And we can get a sense of kind of how dynamic areas are over time, as well as how consistent the algorithms are with each other. And on the left here, we can also track class transitions or the classification for a single location over time. So the top example and the bottom example, these are both points that at some points in the 5-year period are within a continuous with a large lake, and at other periods in time are either dry or have transitioned to kind of a vegetated water. And so in these graphs here on the top, the black dots here are the Palmer Drought Severity Index. And this is just to kind of give you a sense of kind of how wet the site is at that point in time. So you can see here that in the first part of the time period, it's pretty wet, and both these algorithms are mapping this point as open water. And then as the site becomes drier, both algorithms are switching. Sentinel-1 is mapping this entirely as dry, and Sentinel-2 is kind of mapping it half the time as dry and about half the time as vegetated water. And this bottom graph, kind of similarly, the site is starting out pretty wet in the first couple of years. Both algorithms are consistently mapping this point as open water. And then in about 2020, the second half, the site is becoming kind of substantially drier, and both algorithms are switching to mapping this as vegetated water. So kind of mapping takeaways, we've got two surface water algorithms. They can both map open and vegetated water over time. The algorithms are coded so that they can be applied anywhere we want them to be. And the open water is performing well in both algorithms, and the vegetated water is contributing a lot of important data, but we know that it's less accurate and also less consistent between the algorithms. And so our takeaways from this is that how we use the algorithms together just needs to be a little bit thoughtful so that we can kind of keep those any potential inconsistencies in mind. So with an eye towards that, let's switch gears to how we have some of the projects that we have been integrating the surface water dynamic data. And this first one is focused on a climate change project that's ongoing. In this climate change project, we are looking at how climate change may impact surface water dynamics across the central US. And so we're looking at 32 different sites spreading from north in North Dakota and Minnesota, south to Texas and Louisiana. Our premise in this project is that surface water is highly dynamic, that it's responding to episodic events, to seasonal variability, to interannual variability. And so with that in mind, the goal of the project is to project the impacts of climate change on that full range of surface water conditions. And we're looking to project that water time series under two different IPCC emission scenarios. RCP 4.5, which assumes kind of a stabilization of radiative forcing, and then 8.5, which is kind of a more business as usual scenario with a continuous rise of the radiative forcing. And so our first step is to generate a surface water time series for each of our 32 sites. And so if we start at the top of this flowchart here in blue, these are our two algorithms that we just finished talking about. And so for each of the 32 sites, we are classifying all of the imagery within the 5-year time period using both algorithms. And then we're consolidating all of the classified imagery into a monthly time step using a class voting approach. And the approach here is to basically use a majority vote. So if, let's say, that pixel was classified 5 times within that month, then we look at all of the classifications and we assign it to the majority class, whether that's non-water or water, where water is referring to either vegetated water or open water. The only case is if it's a tie in the voting between non-water and water, then we essentially downvote vegetated water and upvote open water because of that discrepancy in the accuracy. And so what you get are some examples here on the right, which is showing the total surface water extent for these areas over that 5-year time period. And because we kind of took that step to go from a single scene to a monthly time step, we also ran and produced a validation of this approach. So we used entirely PlanetScope images. And because we're comparing the validation images to a monthly time step classified image, our validation images were all selected in like the middle part of the month, between the 10th and the 20th of a given month. So you can compare here the accuracy statistics of our monthly water, non-water time step for the central US compared to our scene level validation for CONUS. And so we've got about a 2% omission error, about a 6.5% commission error, about a 97% overall accuracy. And so you can see that we're doing, we've got higher commission error than when we're just doing open water for single scene, and that's because we've integrated both the vegetated and open water. But that the voting at a monthly time step is helping reduce that commission error quite a bit. All right, so we've got our surface water time series. The kind of the next step is to figure out how to model those time series. So there have been prior efforts to start to explore what might happen with surface water and with wetlands in the future, particularly in the prairie pothole region, more so than across all central US. But the primary approach that has been taken to date is to look at wetland density on the landscape and model wetland density as a function of kind of climate normals, and then insert climate change kind of new normals into that model so that you can back predict your kind of new predicted or projected surface wetland density. This approach has two kind of weaknesses. The first is that it gives you information about kind of what might happen with the average, but it really kind of ignores the variability over time. And oftentimes we're kind of interested in the extreme conditions at a site rather than kind of the average condition. The other weakness is that it assumes that all sites are going to respond similarly to climate inputs. From some of our past research, we know that this just kind of simply isn't true. So this is a paper that we published back in 2018. And what we did here on the x-axis is we looked at how surface water responded when you moved from really dry conditions to really wet conditions. And what we see is that some sites show this really big response in surface water extent. And this tends to be sites that are often in the prairie pothole region in North and South Dakota. They've got a lot of lakes, a lot of wetlands, lots of surface storage available. And you have other sites where kind of no matter how much precipitation you dump on these landscapes, you see very little change in the surface water extent. And these are landscapes that look more like this bottom picture here on the right. And that's because most of that water is infiltrating into the ground or relatively rapidly leaving the basin in kind of extensive drainage networks and streams. And so what does this mean? And for this project, it means that we really need to develop site-specific relationships between surface water extent and climate so that we can kind of have a better chance of accurately projecting the impacts of climate change. And so that's what we did. We developed 32 models, one for each of the sites. And we modeled surface water extent as a function of kind of a whole host of grid-met meteorological conditions. All of those variables were then averaged over 1, 2, 3, 6, 9, and 12 months in order to kind of capture kind of the full range of antecedent conditions. And then we applied our climate change projections to the statistical models, where we defined kind of future conditions as 2061 through 2080, and our current conditions as 2006 to 2025. And what that produces is here on the right. And so for each site, you have in black is the original time series, and then you have projections of at each of the emission scenarios in blue, and the gray is representing the full range of model outputs to account for kind of uncertainty and differences between climate models. What this enables you to do is look at changes that are happening seasonally, as well as changes in peak conditions, not just a shift in kind of the average condition. And so on the right here, this is showing kind of some seasonal projections and what's happening on a seasonal basis. So this is actually on the right here, this graph is actually showing you climate change. A lot of numbers, ignore all of the numbers, just use the colors to guide you. So what you can, this is kind of giving you a sense of what we're seeing in the climate data, not our projections, not quite yet. But essentially, we see that temperature and vapor pressure deficit there are latitudinal gradients, but essentially are projected annually to increase everywhere. But the precipitation has some kind of seasonal patterns that are kind of important to note, in that winter for a lot of these Midwest and northern sites, so kind of the northern half, are projected to show an increase in kind of winter and spring precipitation, but a decrease in summer precipitation. So it's almost like an amplification of the seasonal patterns. And that then kind of falls apart in the more southwest and southeast sites, where we've got maybe a few smattering of increases, but for some of these sites, it's just straight declines and becoming projections to become drier kind of all across the board. And so what that means is that we see differences in kind of the directionality, not only between sites, but also between seasons. So we have kind of the most number of sites showing declines, projected declines in water in the summer and in fall. And this is generally attributable to an increase in vapor pressure deficit and temperature with a general decrease in summer precipitation. And then for about half the sites, we're seeing a projected increase in the spring season and nearly half in the winter season. And this is consistent with projected increases in winter and spring precipitation for many of these sites that are kind of exceeding the temperature changes in those seasons. And so this graph is showing kind of how that breaks out geographically. And this is the projected change to water extent. So it's incorporating not only the predicted percent change, but also how much water you just have on that landscape. And we can see that most of the sites across the Midwest in an annual time step are projected to become, to have less surface water than they currently do. There are a few exceptions to that, and most of them are clustered up here in the north, where they're projected to show increases in the surface water extent. And we also looked at kind of the wettest 15% and the driest 15%. The patterns were most consistent for the driest 15%, and essentially about right around 24 and 23 of the 32 sites are projected to show declines in that driest 15%. And that essentially means that the impacts of a drought on surface water will become exacerbated. They'll become kind of worse. The impact of drought will become worse than they currently are. But I think it is very important to note that although regional trends are clearly present, the direction and magnitude of the projected change can be kind of shockingly site specific. And that's likely due to kind of land use, but also wetland type and storage dynamics. All right, we're going to do this one's much shorter, so shouldn't take too much time, but I'm going to show just one last application where we're starting to use surface water data. And I want to include this one because it's fairly close to Memphis, kind of just down the Mississippi River from you guys. And this is a somewhat controversial project, so I'm not sure how many of you guys are familiar with this project at all, but this is, we recently started working with some folks to look at some of the dynamics in the Yazoo backwaters area in Mississippi. And so here you've got the Mississippi River flowing down. This is the Yazoo, Mississippi River flowing down. The Yazoo River on the right here flows into the Mississippi River. And in orange here, this line all around it is levees. So the area is highly managed, and the levees prevent the floodwaters from directly entering into the backwaters. When the Yazoo River is higher than the water level in the backwater area, these two gates, which are the green dots, close, and this reduces water input into the Yazoo and the Mississippi, but then water floods and backs up behind those gates. So there's ongoing Army Corps of Engineers and EPA project to explore different management options to address some of that backwater flooding. One of the big complicating factors is that there is a lot of bottomland hardwood forests in this area that depend on seasonal flooding. So all throughout the Steel Bayou, the Delta National Forest, and the Panther Swamp National Wildlife Refuge. So our research question here is, how would a change in the water management potentially impact the hydro period of existing forested wetlands? And when and where might we see those changes? And can remote sensing inform this? So starting out, this will hopefully look familiar. It's very similar to what we did for the climate change process. We processed the Sentinel-1 and Sentinel-2 algorithms for all of the imagery from 2017 through the end of 2022 for this basin. And instead of consolidating it at a monthly time step, we consolidate it at a 2-week time step, so we can kind of get the most seasonal data that we can possibly get. However, at a 2-week time step, we do have some gaps in the data. And so we then do a gap filling process where we look at the kind of T-1 and T+1 time steps in order to get complete data at each time step. And we get on this upper right here graph in gray is what you get. It's the total surface water extent at a 2-week time step over the 6-year period. And we can bring in independent data sets to check, to kind of get a gauge on the quality of the data. This is the Big Sunflower River. This gauge is north of the study area. And we see that the seasonal dynamics of the daily discharge are matching pretty well with what we're seeing in the inundation. And then we can also start to add in some of the water management data. So in orange, the orange dots here are 2-week time steps in which the majority condition is that the gate is closed or dewatering. All right, and so our kind of next step is to ask what surface water can be at least partially attributed to that backwater flooding. So we can first kind of limit that to inundation that's occurring when the gates are closed or dewatering. But then we want to add a second requirement that water, that surface water be continuous with the backwater flooding. That term backwater flooding immediately becomes a bit contentious in terms of how exactly you define that, and can be kind of challenging to define. As we know, the impacts of closing the gate can kind of propagate upstream. And so this is showing kind of 3 different versions of stream networks and that are using kind of different assumptions about how far upstream those impacts might propagate. And this is the percent of flood-related inundation of total inundation over that time period. So you can see there are kind of big chunks of the Yazoo backwaters where this water is kind of representing a kind of 30 to 50% or even higher percent of that total inundation. And we can also look at that over the time series and quantify that water in relation to the total surface water extent for this area. And kind of what we see, 2019, of course, was a year with a ton of flooding across the Midwest. And we see that the higher the Mississippi and the Yazoo River levels, kind of the longer the gates are closed, the more water backs up into the backwaters and contributes water to the forested wetlands. And so this project is ongoing. Kind of our next step is to explore kind of statistically how the inundation extent is responding to local meteorological conditions relative to kind of regionally driven management actions, but hopefully provides an example of kind of how we can use the surface water data and start to integrate management actions with that data. So just very briefly, in summary, we are finding that multi-sensor surface water algorithms can improve the completeness of surface water data sets, and that we can start to use this data for all different research questions and projects, whether that's informing impacts of management decisions, projecting the impact of climate and of climate change on surface water dynamics, as well as many more. And with that, I'll stop and take any questions anyone might have. Thank you all.
Thank you. So if you have a question, feel free to either write it in the chat or you are more than welcome to unmute yourself. Does anybody have any questions?
Oh no, and I just saw that the slides were not advancing for someone. Uh-oh.
They were advancing, it's okay.
Okay.
Well, all right, I actually have a question. What was your favorite part of this research? Like, what was your favorite part in the methodology or just in general?
Yeah, oh, that's a fun question. Let me think here. I've got a couple. So I sometimes get bored easily. And so I try to use every project as kind of an opportunity to kind of expand my skill sets. And so in generating the surface water algorithms, we kind of were implementing it in the Python API backend of Google Earth Engine, but we slowly kind of ran into the limits of the Google Earth Engine, then we moved there, and then we had to continually figure out what the walls and limits were of our system and how we were going to kind of maximize and get around things in order to get things running. And there was something about that process that I just kind of deeply enjoyed about learning. But I also really enjoy the implied, I sometimes think of it, okay, you've got your classified product, and now you get to do the fun stuff, which is like, what can you do with that data? What questions can you ask, and whatnot? So hard to pick one.
Thank you. Do we have any more questions? All right, well, I have one more. Is there anything in your research that surprised you?
Let me think here. Yes, I think the short answer is yes. In a couple different ways. There's a point in my mind in every single project where you kind of come in with an idea of kind of how the world works. And then there's always a point where you realize your data doesn't quite match what your initial idea of how the world works. And that can be a bit disconcerting, but it's also a really cool period of the project where you're figuring out what the data is actually telling you. And it's usually that your understanding at the beginning was just kind of too simplistic. And the data is kind of saying everything's a bit more complicated than that original simplistic piece. So I think that's probably true for any project, but I would say in the climate change project in particular, it was I've worked on a lot of research projects where you're kind of climate change is a context or a motivation for it, but this was one of my first opportunities to really dig into that data and that world, which I enjoyed immensely. And I think one of the pieces of that I found surprising, but that makes sense if you think about it a little bit more, is that seasonal dynamic and that amplification of it is that the impacts just aren't straightforward, and sometimes an annual average really almost masks the complexity of what's happening, but that there's kind of feedback mechanisms, and that the changes are not going to be even across the year. And so therefore, if you're overlaying that on something that already is showing a seasonal dynamic, that you can have these kind of really interesting impacts that you might not have kind of originally thought about.
Awesome, thank you. This was a really awesome talk, and thank you so much for sharing your research. Do we have any last questions?
Yes, I have a question.
Go ahead.
Do you have a way, or is there any kind of a way to detect groundwater conditions?
Yeah, it's a great question. So there is a satellite called GRACE that actually uses, I believe it's in the name, I think it's gravitational something. I forget what it's called, but GRACE is probably the most popular satellite I've seen for looking at changes in groundwater. The challenge is that it's really coarse in resolution. So you're talking like regional trends in groundwater. So for example, they can detect, in certain regions where they're pulling a lot of groundwater out to irrigate crops, they can see that change over time. But as far as looking at for a project specific basis, it's oftentimes kind of too coarse.
And I will post a link to the GRACE satellite in the chat.
Oh, awesome, thank you. Yeah, and feel free to follow up too with any questions that might come to you later. I'm happy to answer them via email.
All right, any more questions? All right. Thank you so much for your time. And we really enjoyed this. So thank you.
Yeah, thank you all for taking the time out of your day. I really appreciate it. And thanks, Michelle. It was great seeing you again.
Yeah, it was great seeing you too. All right. Thank you all. Or Jiro, do you have a question?
Oh, no, I just wanted to say thank you.
Okay, awesome. All right. Thank you all. Bye.